that invitation, I was thinking on what to present, and well, I'm not yet retired, and therefore I do not have time to prepare any new pitches. So all you see presented, I see somewhere. And we started, I do not know the reason why we started our investigations on multi-action fatigue now nearly 18 years ago or so. I did, others in my group did previously, and well, this is something which has been done at that time. And when we started, we tried first of all to look what happens, and we observed the surface of metallic specimens and applied the replica technique. And this first figure shows you replicas from a later stage of the fatigue process, and I don't know whether the resolution is sufficient here. So this one on the left-hand side is a uniaxial loading of a steel specimen. I think it was with a strain amplitude of something 0.3%. And what we observe under uniaxial loading is a trace of a crack at the surface, and usually it has initiated around some inclusion or so, which we cannot identify on the replica. This is not the real metallic surface of the replica. And then we tried all such things also under multi-axial loading. On the right-hand side, you see also what we find in very, very many of these replicas, trace of a crack, and the fatigue process includes itself. Then we concluded, and many people more before us also saw, that that fatigue process is a process of growth of short cracks from some defects which are inherent in the metallic structure. Right-hand side, you see multi-axial, non-proportional, pseudo-random strain sequence, so all evil things, what you can think about. If you simply look at the surface, you cannot decide which sequence or so this material has suffered from. And therefore, we decided to apply some fracture mechanics-based modeling on that. And being honest, again, we have not been the first one. But we tried it, and as a result, we arrived at some point now where we are maybe too complicated with our models. And during going through our model, I try to identify where are the problems, and I like the title of this workshop, Challenge, and therefore I use it here again. And this is now a list of 10 challenges, let's say problems to deal with, which is incomplete, of course. There might be more, and however, these are the 10 points I'd like to present you. What are the problems and what we did, and what is the actual state of modeling. So it starts here with the crack driving force. So you saw the trace of that crack at the surface, and now what makes it grow? Well, we know from previous investigations with uniaxial loading that maybe some variant of the cyclic chain integral can be used as a crack driving force parameter. These are crack growth rates over delta J effective. I will explain in a minute what I understand under this. And in this graph, you see the long crack scatterband of a certain steel material, and also data points for surface cracks measured during their growth from the point we can see them. Let us say 0.2 millimeters surface crack length, total surface crack length to, let us say, 1 point something millimeters at different applied strain ranges listed here, and well, they go along here. Similarly, very close to the long crack scatterband, and therefore we think that this works at least over several decades of crack growth rates. This is a crucial thing. And what we do in fatigue is that we cannot calculate this J integral by making a path around the crack tip or something like that. Totally out of range. strange, so we very much rely on some approximation suggestions originally brought forward by Darwin, also adopted one of his formulas. So this is now the uniaxial case, and if you see how these approximation formulas are constructed, you see there is always some square of stress, so you can say it is a multiple of stress with strain, either the stress with the elastic part of the strain or stress with the plastic part of the strain, which takes the dimension of a strain energy density, and we had that discussion. And well, if you multiply this by crack length A, you get a good estimate of J integrals. However, this one is now here. If you take a parenthesis and interpret this as a strain energy density, it is a directed one, so there is a crack direction behind that. And well, this is what we take in the uniaxial case. And then we speculated what should we take in the multi-axial case. Okay, complicated. We invented our own formulas, let's say more or less, but others did in the same way. We figured out what is the mode 1, opening mode 1, and according to the opening mode 1, we said, okay, let us identify the strain energy density related to the mode 1 direction, multiply that with some geometry factors of the crack length, and do similar things for mode 2 and mode 3. So, okay, challenge crack driving force. It is not solved completely. There might be different and better choices for crack driving forces. Under multi-axial, let us now say mixed mode loading. So challenge 2, what are now these effective ranges we know from the uniaxial case, that if you have applied a cyclic loading, and here you see stress over strain and the hysteresis loop, and we performed measurements of when does the crack, which is swimming in the material which suffers under elastic cyclic loading. When does this crack open and close? And I mounted a strain gauge somewhere, and I identified then deviations from the regular shape of the hysteresis loop, and if you have such deviations, then you can attribute them to opening and closing, and you will find something like that. That in the lower left part of the loop and the associated stresses and strains, the crack will be closed and it will be open at the top right hand side. Then we have effective ranges. Well, this is what we know. Maybe you keep in mind that this hysteresis loop is one with a strain amplitude of 0.2%. In that scale, S160, and it looks like that. So what should we do now in the multi-axial case? Well, again, we tried to measure that, and at that time, now 10 years ago or so, we applied the replica technique in order to get some first impression on what is going on. And we took replicas of a surface when we have detected such a crack here. And this is an example of the material is suffering under such a butterfly path. So frequency ratio of light, normal and shear strains is 2. This is what happens here. And unfortunately, we haven't been at a workshop on crack tip fields or so, and therefore we couldn't resolve what's going on at the crack tips. We had a resolution good enough to see what happens here in the center of the crack. And I show you now a movie, an animation, where 30 individual replicas during such a non-proportional cycle are mounted behind each other, and then you see a silent movie of the center of this crack, if it works. So, this movie is repeated again and again. So if you see these black things appear, then you see the replica material which is poured into the room, so to say. the negative side of the replicas. And we mounted these individual figures such that the top half of this figure is more or less without any motion. So we identified some obstacles or particles here, so that we see, oh, this does not move. And the lower half is going around here according to this number 8. So you see that if you are able to follow some of these crosshairs here. And now the crack is closed, and while the crack is closed, you see hopefully that there is some horizontal motion of the lower half of the material against the upper half of the material. So although there is closure on the, let us say mode 1, it's not completely mode 1 here, we have a mode 2 component which could be able to drive the crack longer. So it looked like that, and then we had to invent some equations. And first of all, we took the uniaxial equation for calculating crack opening stresses and closure stresses and modified them a bit. So the original version goes back to Newman's famous crack opening stress equations. And for the mode 2 and mode 3 portions of the cyclic loading, we reinvented some efficiency ratios with a more or less complicated formula, taking a threshold of friction into account and adding another material parameter which must be identified and makes the application a bit complicated, but these equations are now available, and this is what we use. And I do not want to go in much more detail today. Number 3. Definition of a damaging event. Under uniaxial loading, things are very easy. You know what happens at the critical location if you cycle that in variable amplitude loading or whatsoever. We have rainflow counting and closed hysteresis loops, and we say this is a cycle, and we have a damaging event for damage accumulation. What do we do under multi-axial loading? Okay, we do that. Cycle identification in the plane under investigation. I forgot to mention that all these things are strictly to plane related algorithms. So all what is calculated now with respect to crack growth is not done in one direction or so. No, we have to search that, and we have to introduce a 5 degrees or so step going through the calculation and repeat them, and then at the very end have to figure out which life was the shortest, and do this now in the plane under investigation, identify individual cycles using rainflow, although we know that it might not be appropriate, but we do. Number 4, stress-strain paths under multi-axial loading. Again, first, uniaxial loading. This is a revision of the case now. Uniaxial plasticity is more or less simple. You have to identify your hysteresis loop branches or something like that, and then you mount one branch to the other, and this is nothing else than breakflow. That's it. However, under multi-axial conditions, you need something like a complete plasticity theory, incremental plasticity, and you have to solve incremental plasticity differential equations in tiny numerical steps. Okay, we did that. By the way, my PhD candidate invented his own plasticity model, which I did not promote at the beginning, but he did, because researchers must be allowed to do whatever they think what is correct, and we did. And later on he made such a presentation like here. I will show you here another animation on the right-hand side, and again, the input is a butterfly path under strain control, is shear strain and normal strain. Here is the time sequence. Sinus form. Okay. Nevertheless, what you see here is the experimental result in this dotted line here. And you see there is a breakdown of symmetry, although in the strain space you have a symmetric behavior, or you put in the symmetric behavior. In the stress space, then the symmetry is somehow lost. This is an answer measured in thin-walled tubes. And the red ellipse here is the Mises yield surface, and what I'm going to show you is now the calculated stresses with the plasticity model starting here from the origin and going around somewhere here. And well, you see then this magenta line, which is a calculated stress path, and here around the origin you will see some blue points circling around, which is the actual location of the max stress tensors. It is an extension of the Chaposh model, if you say, or the Chiang model, which was invented somewhere in the Champagne. And well, we don't want to talk too much. So, integrating all this equational stuff finally ends up in such a path. Here, this is the actual path calculated, going up, here and down. Here you see these backstress tensors. We used 5 backstress tensors. You see under these butterfly path conditions, as long as a point is on the yield surface, you have plastic deformation. Now, for example, here at that location, the point dives through the elastic portion of the stress space and so on. And the final end, my student managed to arrive at some reasonable strain and stress amplitudes, although the complete path is not reproduced perfectly, but we said it's enough now, it should be sufficient. Number 5, mixed mode hypothesis. I really am not aware of any mixed mode hypothesis, and we didn't invent really our own one. We simply postulated, and I'm hoping for better suggestions, that the crack growth rate could be added up by around 1 related component, and around 2 related, and around 3 related one. And that's all what we do. We may argue on that. I only have thoughts on what we could do in the future if our computers are a bit faster again. We could start, for example, to calculate these J integrals by a real path integration around the track tip. And we started with a simple example with a feasibility study more or less some years ago. It turned out that everything what I show you then on the right hand side was for an engineering purpose path independent. So we arrived at the same result when calculating around 3 different paths. So this is quite a nice result, intermediate. And what we did is we took a thin board sheet. This is only calculated, no experiments behind that. We have a crack here. We apply normal stress, cyclic, and shear stress is cyclic. And then we put it under cyclic and calculate what comes out while integrating around the crack tip. And the top here is for proportional loading. And here, maybe too small to see it in the back rows here. This is proportional loading with red line is normal stress and green dots is shear stress. And if you start calculating that J integral step by step until you reach that first reversal point, then you get a J integral. This is used for nothing. You can throw that away. If you have identified a reversal point, you have to restart that calculation now again. So this is a new origin here. And then going from here to there to the next reversal point, these J integrals, they increase and increase. If we would continue to calculate J integrals after this reversal point, then the result of the J integral would go down. So you will reach a maximum in J integrals, and this is the indication to stop that integration now. So this is a half cycle here. The next half cycle gives you the same answer. It goes from here to there, then from here to there, and so on. So for a half cycle, you can identify by integration some path-independent value, which we plain chain integral. That's it. And the astonishing thing is that we tried that now also for non-proportional loading and integrated. And well, at the beginning, you can do that nonsense and then throw it away. However, you will identify a certain time step where the chain integral, if continued with the integration, would decrease. Then we restart that, and we get the next half cycle. And again, at reaching a maximum, we restart it again and restart it again. And what comes out is a path-independent value so far, which should have something to do with the active field and should be decisive on the track growth rate. And it also works for butterfly paths. Very astonishing. And as I said, nothing is done with that until now. However, maybe in the future we will continue with these investigations. Number 6, identification of critical locations. Well, it is easy and more or less easy on the uniaxial component, and you can identify where tracks will initiate. Under multi-axial complicated conditions, you have your individual loading cases and so on, and you can solve them. And then you do not know anything. The only thing to do is search. And the searching algorithm is one which goes back to Kripke, Barkey, and Saussure. The chairman says I do not have time to explain that in detail. We checked that for a notched shaft here and found that it's working quite well. So the results later on will be reported for notched shafts. Number 9, size effects. We discussed that previously. We have two kinds of size effects. One is a statistical one, and the other one is a fracture mechanics based one. Actually, we have some Weibull model-based equations for introducing the size effect. In the end, small volumes are starting with their crack growth and shorter crack lengths. This is extracted from scatter and Weibull statistics. Number 9, sequence effects. Well, here now I have a variable amplitude loading sequence. Large hysteresis loop is for 0.5% amplitude, and you find here inserted the amplitude of 0.2%. And again, you identify crack opening and crack closure, and you see that the small cycle, 0.2%, is completely open. And if you do not take care of that, your predictions will be totally wrong. So we copied what we have learned under uniaxial conditions to the multi-axial simulation. And the last point, sequence effects to be addressed are related to impedance limits and such things. We all know as the crack grows, well, if you have a threshold or something like that, first of all you have an increasing threshold due to this short crack phenomenon and so on. And we arrived at some modeling equations to take this into account. Results, last figure more or less. We are lucky enough that there are not too many data in the literature to supply us with all our constants which we need to apply it. So in 2011 we did it for our own experiments, and in 2013 we found that in Germany, due to a research program, more results have been published which we can use to check our algorithm. In common, all of these results is that they are results experimentally on shoulder shafts under non-proportional variable amplitude, nominal normal stress and nominal shear stress, with a phase shift of 90 degrees between them, a pseudo-random sequence with Gaussian cumulative frequency distribution. So all evils of the world put together, experimental results are dots, and our calculations end up in these lines. So I conclude from this that whenever experimentally determined and numerically calculated fatigue lives match under these specified conditions, then the errors immanent by coping with the 10 challenges must have cancelled each other. Thank you.
Thank you very much. Very interesting and very deep presentation. Last slide, please. explain scale, Axel? What kind of slope? Because only 10, 10, 10. What is